region. So we saw that, of course, you can be non-ergodic if you have just energy barriers in classical systems, but if you have quantum mechanics, then you have to impede also the tunneling, and that's done by Anderson localization. So we saw that if you make sure that you don't find the resonances nearby, then you can try to tunnel under the barrier, but if the barrier is too high, then the matrix element will be too weak to tunnel over, and if the tunneling is not resonant, that means if the matrix element is smaller than the level splitting, then you will still not admix and you will not diffuse over there, right? That's the essence of Anderson localization. And then we looked a bit more quantitatively into this phenomenon. We took a lattice model with disorder potentials of the size W and the hopping T or J yesterday. And if you do it very naively, then you just look at the resonant pairs of sides and ask whether they more or less cover the lattice, whether that percolates, and that would give you this naive estimate that you need more or less a finite density of the order of 1 over the dimension of the lattice to cover with resonant dimers, and that gives you an estimate of the critical disorder that you need. But if you are a bit more sophisticated and you allow for resonances at further distance, then you see that you have sometimes small denominators, and that gives you an extra space here, that you get an extra logarithm of the dimension, or actually of this connectivity constant. So it's actually a bit harder to localize when you allow for further resonances. So, okay, and then what is the phenomenology? If you are above this critical disorder on a lattice, then you get localization. That means the wave functions, the eigenfunctions of the single particle Hamiltonian have more or less this qualitative shape. They are centered around some position in space, and then they decay in the envelope sense exponentially with the scale psi, and that's called the localization length. This diverges as you approach the critical disorder. When you are at the critical disorder, these wave functions look very interesting, actually. We're not going into that, but the wave functions are neither localized nor very plane wave-like. They are actually fractal objects and even multifractal. So if you look at the moments of this wave function psi that's the probability amplitude, and if you take here an extra exponent and you ask about the histogram of this thing over space, then you find a very interesting multifractal structure. Then if the disorder is too weak, you approach the clean limit where you get plane waves, and the wave functions look more or less like distorted plane waves, but they extend in space. And if you do the initial value problem here and you put the particle at the origin, then eventually it will diffuse out, and there will be a diffusion constant bigger than 0, and here you have a diffusion constant that is 0, and here you have anomalous diffusion. Actually here the L of t doesn't grow like t to 1/2, but actually t to 1 over d, just for you to know. Okay, so this is what happens on a lattice. That's a very nice dynamical phase transition with an enormously rich behavior at criticality. Yes, please. Mm-hmm. Yes. How you mean in the mathematical sense? Well, I'm not even sure how you exactly formulate that. So I think to talk about point spectrum and continuous spectrum, you have to have some interval of values, and this is if you have a lattice model, then Okay, then you can ask at which disorder do I localize all the levels, but you can go a bit below that level, and then there will be an energy in the middle of the band where you're still delocalized, and then other states that are localized, and there's a mobility edge. And the critical wave functions sit exactly at this mobility edge, and that's basically a measure zero interval. And so I'm not sure it makes sense to talk about the spectrum there, but maybe it's this exotic spectrum. How is it called? Somehow singular continuous. But yeah. Okay, I'm the wrong person to ask this question. But what you might want to remember is that if you look at the spectrum here of the Hamiltonian, then you see clear eigenvalues that come with normalizable wave functions. So that's called a point spectrum. And especially if you look locally in space, you see only spectral peaks at the energies corresponding to wave functions that overlap with this point in space. So at a given point in space, you have roughly psi to the d wave functions that overlap with that space point. And so if you look at the local spectrum, you see a bunch of delta functions whose number is about psi to the d. And then there are a lot of smaller peaks that come from wave functions that sit over here and have only exponentially small weight here. If you do that here, and if you think of the clean limit where w is 0, then you see just a continuous spectrum. You see just a band of states that goes from more or less minus the hopping to plus the hopping in one dimension, right? So here you have a continuum of a continuous spectrum, and here you have a discrete spectrum or a point spectrum. And by studying the spectrum, you can actually also detect localization. It's not necessary to look at the wave functions. You can also just diagonalize and look at the spectrum of eigenvalues. And if you have a discrete point spectrum, the eigenvalues will not repel each other because eigenvalues that come from wave functions that are far apart in space do not know about each other, and they can come arbitrarily close. Whereas if you have extended wave functions, there is always level repulsion. So two eigenvalues don't want to approach because there's a large probability that you have hybridization, and then the eigenvalues repel each other. And so if you just look at the spectrum, you can usually also detect whether you're in this case or in that case. Just as an aside. Okay. So this is, we did that on a lattice, but then you can say, well, real world is in real space. There are no lattices actually, and so we could think of a potential in real space where x is anywhere in r to the d. And then to get to an effective lattice model, you would just say, well, my particle shall have an energy E or EF, a Fermi energy, and that gives me a Fermi wavelength of E. And I coarse grain the system at this wavelength, and I build an effective lattice model with that lattice constant and with an effective hopping, which is just given by the energy roughly, right? And then I have this disorder potential. So I average the disorder potential on that scale, and then I get the W effective. And what you see is that the effective so this is some sort of integral over Vx over some lambda f to the d. Right. What you see from that is that if you increase the energy, it's like increasing the hopping, and so this ratio here becomes smaller and smaller. And so in the continuum, when you're not in the lattice, you can actually tune the ratio across the transition by changing the energy. Right? So especially in higher dimensions where we don't have to worry about these special effects that I talked about yesterday in the end. So in dimension larger than 2, there's always a critical energy such that when the energy is bigger than this so-called mobility edge, you get delocalized wave functions. Yeah. Oh, sorry. That's sort of a smeared, a coarse-grained version of this Vx over a cell of this size. Yeah, it's not since it's not so important. I didn't write it big. Okay. Right. So in 3 dimensions and higher, when you go to high energies, you always delocalize in the continuum. Okay, because disorder is sort of finite, and the hopping or the kinetic energy is growing and growing, and at some point you don't care about the disorder anymore. And only in 1 and 2 dimensions, where there is this special effect that you like to backscatter, eventually this backscattering is taking over, and that's a very subtle effect. But in higher dimensions, you always have this mobility edge. And now that means that the full spectrum in the continuum in higher dimensions is never localized. So if you want true localization of everything, so you want nothing to move far away, then you have to make sure that that this mobility edge doesn't exist, and that means that you should somehow restrict yourself to a lattice, or you have to say, okay, I have some a crystal, there is a lattice that determines where my sites are. I forget about the fact that if I excite to high energies, I don't see this lattice anymore, and it's free space. I restrict myself to this low energy space, and then I have a lattice, and then I'm in this case. And in this restricted world, I can have full localization. But you always have to remember that these are approximations, idealizations. So in the real world, there is no full localization. After all, we are walking around, right? So so when we talk about many-body localization, it will ultimately always be an idealization where we make some approximation somewhere and neglect certain high-energy effects or so. Good. Okay, so I mentioned this mobility edge in particular because in many-body localization there is the talk about many-body mobility edges, and we'll have to discuss in detail whether that exists and how it manifests itself. Right. So other restrictions that are of course popular is this is always talking about quantum particles that are moving around, but you can now say I want to look at quantum particles, electrons that don't move at all, that are always sitting on the same atom, and the only degree of freedom that is left is their spin. And then I come to spin models, right? And that's still interesting because the spins have exchange or they have dipolar interactions, but the charge is not moving anymore. But there we have the added feature that now we don't have these bands and we don't have this continuous space. We have spins on a lattice on these atoms, and they just interact with each other. And then you can ask nice questions again about the spin dynamics. Is it somehow localized or is it somehow diffusive? And diffusion here means then that either spin is diffusing, that means magnetization, or energy is diffusing. Of course, not the particles that make the spin. Okay, and so the more you restrict yourself in the Hilbert space, the more chance you have to get something like many-body localization. Good. Okay. So I hope you get the flavor of Anderson localization, and that is something very interesting. But I was on the way of destructing Anderson localization, saying that this is just a single particle effect, and the textbook usually will say, don't worry about this, this is nice single particle physics, but in many body problems you shouldn't worry about this. And why does it say so? So again, we had for the classical route to non-ergodicity, we had barriers, and then we had this Anderson localization. And I want to kill both for you, and then we rebuild the temple, and then we destruct the temple again, and then we rebuild it again. And in the end, we'll have many-body localization. So what is we said we can be non-ergodic classically if we have barriers. So how is this going to to be destroyed if you have many particles. Do you have an idea? So if I said yesterday, if I have one particle in a well like that, I can never get over here. But now if I put 10 particles in here, would you still buy this argument? I put 10 particles, each has this energy here. Is it still true that you cannot get over the barrier? Well, no, it's not true, because if there are interactions, then this particle and this particle can give their energy to that particle, and then it can go over, right? So if this barrier is finite and I have infinitely many particles because I'm in a thermodynamic system, of course this is a kind of strange sketch then, but then I can get over the barrier, right? And I just have to wait long enough until the energy is redistributing itself in a somewhat rare fluctuation, and then the particles go over, and after some time you have the particles left and right. Okay? So that's why usually you don't worry about such finite barriers. But where is the loophole here? You certainly know about non-ergodicity in statistical mechanics, no? What is the standard example of something that is truly non-ergodic? Yeah, so then, and more sophisticated is spontaneous symmetry breaking, right? When you have spontaneous symmetry breaking, there are two wells like that, and this well is spins more up and this spins more down, and in finite time you just never go over there because it takes you exponentially long in the volume. And what is going on is that the barrier is now proportional to the system size in some sense, usually an interface or so. But so when this barrier grows with the linear size, the linear dimension of your system, then you become non-ergodic, right? And we all know about this. Say the Ising model has this transition, and then you become non-ergodic, right? And that's of course the basis of classical memory, right? So if this is up and this is down, then and if this takes exponentially long to go over here, then you can store your information in there. Okay, no big deal. There is non-ergodicity in thermodynamics, but it's a classical type of memory. So if I'm in this state or in that state, I have just the information 1 or 0, right? But I can never hope to store some quantum phase here. I cannot make a superposition of this state and that state and hope that the relative phase of this superposition is going to be preserved over time. That's just completely unrealistic. If there is the slightest external field that couples to this magnetization, it dephases the relative phase, and you can forget about quantum memory, right? So it's all good for classical non-ergodicity, but not for anything quantum. Okay, fine. Now, apart from spontaneous symmetry breaking, there's essentially nothing that prevents ergodicity, and that's the standard textbook thing that you all know well, I guess. Now, Anderson localization, how is that usually killed? Why should you not worry in a many-body system, as you are usually told? So for this, we have to remember what is behind Anderson localization. So we have in this one-dimensional space, we have these various sites, and they have local potentials, and we have the hopping between this. So this is energy. So these are these epsilon i's, epsilon 1, epsilon 2, and they have this dispersion in space, and then there's this hopping, right? And Anderson localization came from the fact that if the hopping is too weak as compared to this spread of energies, then the wave functions localize and do not hybridize. And that the issue is that there is too much energy mismatch between adjacent or close by levels, and that you cannot bridge by this small hopping T. But what if you have now, say this is if you have one particle here, what if you have, and another particle sitting here and it interacts with this particle. Well, this interaction can give this particle the energy this guy has. You promote, rather you give your energy to this particle, you promote it up here, and you go down here, and you almost preserve the energy, right? And and this will have a matrix element that is finite, and if you have sufficiently many neighbors that can make such transitions, then you find maybe a transition that is so close in energy that you don't have this problem anymore of mismatch of energy. Okay, so if you have, if you have epsilon 3 minus epsilon 4 almost equal to epsilon 1 minus epsilon 2, then bingo, then you're done, right? Then you can make this transition, and now the particle can go over here in a resonant process, and then this Anderson localization is gone. So what is happening in technical parlor is that this particle here dephases this particle. It gives it actually its energy, it changes the sort of the phase of the wave function here, and this interference phenomenon that Anderson localization is actually gone. You can really start scrambling your wave function. So you allow resonant processes to happen again that previously weren't allowed, right? And so from this kind of picture, we say if the interaction is sufficiently strong, and we believe it to be strong, then you get dephasing from energy exchange with other particles, and that will restore the diffusivity. Okay. And maybe you notice that the way I explain it's sort of difficult because it's not really convincing. I mean, you wouldn't believe it to me really if you think about it, because I need some neighbors here that have this condition, and how much approximate can you afford here? That depends on the interaction. If the interaction is extremely weak, then I have to be extremely precise, otherwise I'm still not resonant, then the amplitude of doing this will be extremely small. So you can imagine that if you tune down the interaction to zero, not even that will help anymore, right? And that is exactly the loophole where many-body localization comes in. So many-body localization is the idea that if I make this order sufficiently strong such that all these energies are pretty big, and I make interactions weak such that I usually cannot have this situation, then I can still not restore diffusivity. I can still not make resonant processes anywhere in the system. Or if it happens somewhere, it happens only locally, and then it doesn't affect you at large distance. And so if it happens over there, maybe there something can move a little bit, but here I cannot do anything. And if that happens, so if this order is big and interactions U are small, is small, then there is maybe the chance of many-body localization, that all resonances or most resonances are killed. That means the matrix elements of the interaction between non-interacting configurations will be too small as compared to the energy differences that you still have. So if you see, if you make this transition, then you have an energy mismatch which is of this size, and if that is still bigger, so if this is bigger than the interaction matrix element, so U between, say, you start from 1 and 4 and then you go to 2 and 3. If this matrix element is smaller than this mismatch, then this is just a perturbative admixture, and then it's like in the in this double well problem that I showed you yesterday, where this mismatch is basically this bias, and this matrix element is like the tunneling here. If the tunneling is too weak, then you only perturbatively admix something like this, but you never go really over here, right? And now the whole art of many-body localization is to turn this picture into something more convincing and to go beyond, right? And to really convince yourself that there are no loopholes when you go to higher orders or to further distances and so on and so forth. And that will be the plan for the over next step. I will give you more of intuition for that and some qualitative first perturbative arguments like yesterday, and then some more rigorous ideas, and then I discuss also the caveats and the real dangerous things that happen when you are really devil's advocate. And then we'll see that it's actually not as simple as it looks there, because this kind of cartoon you can draw in any dimension, and it seems dimension plays no role whatsoever, and that if you make the interaction extremely weak and short range and everything looks like it is pictured, then you will always get many-body localization if interaction is infinitesimal. That looks almost obvious, maybe. But that's not true, actually. So things are more subtle. And that was only realized recently over the years. But if you say many-body localization is just a survival of localization to weak interactions, it is more or less true at the qualitative level, and the reasoning is just this. And so if you retain that, you understand already quite a bit about what many-body localization is. Okay, but now I think before we go further into that, I should tell you what happens if this is not happening. Because if the interactions are strong enough, then what can you say? Then you can say, well, this Anderson localization is destroyed by dephasing. That means you have the possibility of resonantly getting some energy from your neighbors, and that is somehow nothing else than to say that here is my system, and here is all the rest of the subsystem, and here is all the rest of the system, and the rest of the system acts like a bath with which I can exchange energy. And as long as I can take any energy that I want from the rest of the system, then of course I can always bridge these energy differences, and I can always make resonant transitions. So if I think of this as subsystem, and this as a sort of the bath part for this subsystem, then the question of many-body localization is, does the remainder of a subsystem act as an actual bath for the subsystem, yes or no? If it does, then you have a diffusive, ergodic, thermalizing system, and you are happy, and then you don't need phonons or whatever, you don't need a thermal bath to connect to your system, then it's its own bath. But if this condition here is usually not satisfied, that the interactions are not strong enough, but if you are in this condition, then the surrounding will not be the bath of subsystems, and then you don't thermalize. Okay, and then if you don't thermalize, then you retain memory of where you put your particles initially, and that's an interesting thing. Then you retain patterns to infinite times, and you might even retain quantum phases, because if you don't have anything to exchange much energy with, then you can hope that you retain phases to some degree, at least. Not completely, as we will see, but to some degree at least. It takes much longer to lose your quantum phase, and so that paves the path towards having quantum memories. So to fully appreciate what it means not to thermalize, I think it's important to discuss what thermalization actually is. So because that's also quite an interesting, an interesting phenomenon by itself. So far, people, until maybe 10 years, 15 years ago, people were completely in the framework of thinking that you're always in this situation. Or they were saying, well, in the solid state, we anyway have phonons, so why would we ever care about, the closed system of electrons that do not feel phonons, that just doesn't exist. But you could have thought of nuclear spins, for example, that couple extremely weakly to phonons, and actually that was happening in the 70s, and people were talking about sort of thermalization or many-body localization in nuclear spins, but it has not really percolated too much in the community. But say the general framework was there's always a bath, so let's not worry. But now we have cold atoms and all these artificial systems where there is a priori no bath. There is just a quantum system that you're interested in and nothing else. And so the question whether the system is its own bath or not is an interesting one to study. But if the system is its own bath, then how do you go on? What do you do? So you say basically you have to determine what is the rate of transitions of your single degree of freedom that you're looking at, your spin or your electron that wants to go over here. How do you calculate the rate like that? Do you remember how you do that? If you want to say you have a spin system, the spins interact with each other, and now you want to know what is the spin flip rate for how long do I see a spin up when it interacts with others? What would you do there? Exactly. So there's this, here we're in the right place for that, right? It was maybe invented here. There is the Fermi golden rule, gives transition rates. And it's very important to for single degrees of freedom, right? Let me write down how this goes. Say you have you want a transition from initial to a final state, right? And you ask what is the rate for that, and that is 2 pi over h bar, right? Then you have a matrix element from I to f, initial to final state squared, and then what is missing here still? Yes, exactly. So something like a delta function, and then you have a sum over f, right? And then usually people take this sum and make it a continuous expression. You write something like a density of states here, right? Now, can you always use this expression, or when can you actually use it? Have you thought about that? Say, if I have just 2 spins, right, and I ask when does this spin flip, and then I say it interacts with that spin. So, can I use this expression? If I just have 2 spins and I ask when does the first spin flip, is this expression of any use? Or why is it not, if not? Well, look, I mean, you have to think what is the initial state. So say, for example, the first spin is up, and the other spin is in some state, say up or down, and the final state shall be this spin flipped, and the other state, whatever, also up or down. But there is only a discrete number of final states, right? And there's a delta function here, and the sum over discrete delta functions is essentially always 0, except except if you have an exact degeneracy in your spectrum, right? But generically this will not happen, and so this is just zero. What does it mean? That means the spin cannot really flip. It can, if you just have two spins that are interacting with each other, they form some 4 eigenstates, right? And then the motion is quasi-periodic, but the spin always comes back to where it was. It will never flip and never come back, right? So this expression makes sense only if you couple to actually many more degrees of freedom here. And if these degrees of freedom not only are there, but they are also coupled in such a way that you get a continuum of final states here. So for example, in the textbook you will probably think about an atomic decay or some ionization process or something, and there you always have a particle that goes out to infinity, and so the final states are all these plane waves that go far away. And you can think this is an infinity of particle positions, so this is a continuum of states that you can couple to, and so this sum here becomes an integral over positions, for example, or over momentum. But if you have just one other spin, there's just a sum over 2 or 4 states, and the transition would be 0, right? So that's a very basic but very important observation. So when you now say I use the golden rule here, what are you actually assuming? You're assuming that the neighborhood here forms a continuum of states, or that you see it as a continuum. But as we discussed in the Anderson localized case, if you look at the local spectrum of a non-interacting Anderson system, you just see a few delta peaks. That means there is no continuum, there is only discrete energies that you would see. So if you take an Anderson localized system, you put very weak interactions, then essentially you can only connect to final states that have very sharp energies, and they are some delta functions. And if you write down an expression like that with almost certainty, you would get 0, right? Because you cannot conserve the energy. So if you say the system is its own bath, then you're implicitly assuming that here the Fermi golden rule makes sense, and that you have a continuum out here, right? But that's a self-consistent problem somehow. You have to first establish, is this really a bath? Is this a continuum? And then you can use that. And until 15 years ago, people were just saying, well, that's sort of, how could it be different than that? But it's not obvious. It's not obvious. If you have, of course, phonons can never localize, as I told you yesterday, these lattice vibrations, they are always coupled in space. They are very insensitive to disorder, and so this is always a continuum, and that's why lattice vibrations, phonons, always delocalize. They are always forming a bath. You would always have a continuous sum here when you have phonons. But if you have just spins, for example, or discrete electron states, then it's not obvious that this becomes a continuum. And so one way of approaching MBL is to establish when is this stuff out here not a bath, right? And then you, under these conditions, you can say it looks like the system is not its own bath, and then you're localized. So that was the first step that was taken 15 years ago, and we'll go through that after I discuss thermalization. And then you will see somehow, then you get a better feeling of when does this really happen. But, so if you can establish that this is self-consistent to say that this is a bath and that this forms a continuum, then you get sort of these collision rates, so or decay rates. So there's a collision time or a decay rate, and so in a standard system, this goes to 0, but only when temperature goes to 0, and that's the condition that you need to have a standard insulator. So when people were discussing about insulators before, MBL, they mean something like this: a system where the collision rate or the transport time becomes the inverse transport time becomes 0. You have no collisions, and if your particles that you're looking at are local, say spins, then there is no transport until you have a collision and you can flip, right? And so standard insulators are then just systems where, for example, the thermal conductivity divided by temperature, say, or the electrical conductivity tends to 0 as temperature goes to 0. And that is relatively easy to have. So if you have an Anderson insulator, even with phonons, the phonons can help you to make transition between localized states. So you take a phonon, you take its energy, and you promote your localized state from here to there because you can bridge this energy. There's a certain matrix element for that. But you have less and less phonons at low temperature, and then you need a certain energy to do that, and so this becomes less and less efficient, and so the conductivity goes down, and also the heat conductivity goes down, and so you get what is called an insulator. And that's, of course, a very old story. This was understood even in the 50s or so, or even before. But that's not what MBL is, right? MBL would say at a given finite temperature even at finite T, you would have this collision rate or decay rate equal to 0. So if your environment acts essentially as a finite system like here, then this formula makes no sense, or it essentially is equal to 0, and you have no decay. You can only have decay if you couple to infinity efficiently. If you can get energy away and it diffuses away, or you take energy and it comes back from infinity, then you can have transport and equilibration, and otherwise not. Otherwise you just see local redistribution of energy, and it jiggles back and forth, and but nothing is really transporting and diffusing. So MBL says this is possible at finite temperature, and in a lattice model even at infinite temperature on lattices, because on a lattice you have a finite bandwidth, say for example, your spins can only have a certain amount of energy per lattice site, and so if you go above that energy with the temperature, nothing much happens. That's equivalent to infinite temperature. And so you can even talk about infinite temperature and the absence of transport there. Right. So. But people before MBL were still very interested in that, and then you can ask what do interactions do to an insulator like that? And of course interactions don't just do nothing apart from providing a bath. They also can renormalize disorder, they can renormalize the density of states and so on. But at low temperature, they just renormalize basically a single particle problem, sometimes in interesting ways, and then you get interesting laws of how this goes to 0 as a function of temperature. So the RG treatments, for example, how you flow to of strong disorder flow. So when you get localization in the effective low energy theories that arise. But that's not the same as what we mean by MBL. But just to say that there is a whole story of kind of zero temperature physics or very low temperature physics that could also be seen as interaction and localization, but it's not what we mean by MBL. MBL is really the absence of any transport and equilibration, whereas in these systems you always equilibrate on long times at finite temperature. Good. Any comments or questions at this point? Yeah? But what do you mean by weak dephasing? Yeah? No, but off-resonant process means that it's only a virtual process. There's only admixture, but there's no true decay. So you can never say, now I'm over there. I just admix that in a coherent fashion, but it's not that I forget about where I was. You see? So these resonances are important that you can say now the particle is really with substantial weight over here and then later over here and then here. If this is weak and then this is also weak and this even weaker, then this is exponentially decaying. You have some small amplitude of seeing your particle over here, but it exponentially decays and it never grows in time. If you have resonant processes, then this will really move, and as a function of time, it diffuses. So this is a true important difference. Yeah. Well, think about maybe the Anderson problem, right? There it doesn't grow in time. Then that probably you understand pretty well, no? Then there are these wave functions that are localized. You see that they have exponentially small weight out here, but you're always coming back, right? There's always, nothing forbids you to add a little bit of amplitude further out, but your amplitude back there where you started always remains big. You don't entangle with other degrees of freedom that allow you to move away somehow. Yeah. Yes? Mm-hmm. No, it doesn't. Well, that just means that the energy is at the most likely energy that you have in this Hilbert space, and still there is now no theorem that tells you that you have to have transport. For example, if you have an Anderson model, the sufficient disorder, no interactions, if everything is localized, there is no transport, no thermalization. Yeah. But this notion makes only sense if you're on a lattice. If you are in the continuum and you have unbounded energy, then this will never happen, right? Because then there's always a mobility edge at high energies. You're delocalized, and so if you go to sufficiently high temperature, everything conducts. So this is only in the idealization of a lattice model that it makes sense. If there are no other questions, then let's take a break now until maybe 10:05. Yeah? Good. Okay, so to fully appreciate MBL, we should maybe define it as what it is not and understand thermalization a bit better and sort of demystify also what thermalization exactly means. So at the bird's perspective, what you would usually say is if you can use the golden rule and you have decay rates. Okay, so there's some characteristic time over which you start colliding and changing your system, and then it starts at small scales that you start equilibrating. That means you start establishing some local equilibrium, meaning local temperature, local chemical potential, and then maybe in different places in space you have still different temperature, and then you have a temperature gradient, and there is heat flow and diffusion and so on, and at longer and longer times you have more and more homogeneous situations, and that is described usually by hydrodynamics, right? You write down the equation for heat conduction, the heat diffusion equation, and at that point you're pretty classical in the sense you're not worrying about the individual degrees of freedom anymore. What they are really doing, you're just describing the state of the system with local thermodynamic potentials or parameters like temperature and chemical potential, and then you ask how they evolve in time, and that looks pretty classical. And over long times you will approach the global equilibrium. But if you think more deeply about it, about this thermalization process, which you describe in this way, and this is correctly described in this way, you can think really about the quantum many-body dynamics, and it's a sort of an apparent paradox, right? So you start with an initial state, whatever you want, maybe a pure state or a mixed state. Let's think about the pure state, right? And now you let it evolve over time. It's a closed quantum system, and the evolution is unitary, right? So no information is lost, the norm is preserved, and yet in the end you say the system looks completely dull and has just maximum entropy. What does this actually mean? You have lost information somewhere. Where is the information gone if the evolution is unitary? Right. Exactly. So the information is not lost, but it is hidden in completely global correlations between all degrees of freedom. And even though it's there, maybe if your system is small and you have it on the computer, you could still retrieve it. But I mean, there is no measurement that can measure these multi-point correlations that would tell you there is still this information of the initial state. So it's kind of hypothetical that it is still there, or it's just impractical information. And so it's the unitary evolution that takes the information to unmeasurable degrees of freedom. And if you look locally, because the information is globally distributed, then you don't see it anymore. And that's how thermalization can occur. Okay. So in particular, if you have a big system and you look at a certain subsystem A, and here's the system without A, then this looks like a reservoir for A. And what you should look at is the thermodynamic limit. So you want the volume of the system to go to infinity. And then you look at some, say, an initial state of the whole system, psi at t equals 0, or you can also take a density matrix, which would be, you can take some sum over pure states, whatever you want, and then you time evolve. And what we would be interested in particular are states, initial states that are not anywhere close to equilibrium, but maybe have some big gradients in density or in energy density. And then we ask what happens under the time evolution. Okay, so potentially very inhomogeneous. Okay, and then right. And now what one usually does is one picks out the region that you want to observe, and then you say, I don't care about what happens outside, so I trace that out. That means sort of I have no information of what is out there, and I average of what is there, and that is done by taking the density matrix, the reduced density matrix, which so the density matrix evolves in time. These states have a time evolution, or this one. If you have a pure state, the density matrix is just psi, right? And that evolves in time. And now you trace out all degrees of freedom outside of A, and that's the reduced density matrix. And that captures all the correlations that you need to know in the system, in the subsystem A density matrix. All right. Good. And now to say what thermalization is, you compare that reduced density matrix with what you would get in the Gibbs ensemble. So the Gibbs ensemble, you say the full density matrix the full density matrix of the system would be e to minus h of the full system over temperature divided by z. And so you have to compare this guy here, rho of t, with the, of course, also traced out Gibbs ensemble. So right. Okay. And so a priori it's not at all clear that there is a connection. So this would be the equilibrium density matrix of A, reduced density matrix. And now thermalization is the statement that means that rho A of t goes, when t goes to infinity, and also in the infinite volume limit, appropriately taken together, goes actually to this equilibrium density matrix. So even though in principle no information is lost in the whole system, if you look at the subsystem, you forget all this information, or you cannot retain any of the initial information, because you need information that sits outside and that you throw out, and so you lose this information. So if you look at A, you see the equilibrium density matrix. Yeah? Yeah, I understand that it's sort of philosophical, but I don't exactly understand what you want to ask. So I'm just saying, if one says thermalization is happening, one means this, and the question is, does this happen or not? In many systems, so that are not MBL, this actually happens, or is believed to happen. If you do it numerically, you see this very well. Or maybe can you Yes, right, yes. Right, I mean, so the subsystem is not infinitely large, it's not half of the system, it's a small part, and it will remain small. And yeah, I don't find that so particularly interesting. I just want to mention that. So now there's a hypothesis known as the thermalization hypothesis, that almost any initial state which has a given total energy E, and which is not too crazily distributed in space, more. Yeah, let's forget about the fine details. Almost any initial condition with a given energy E will eventually have this property, right? So you distribute your energy like that or like that, and if you wait long enough, maybe you have to wait, the diffusion time, of course, of this volume. But after that time, you will just see local equilibrium in any subsystem. It's kind of spectacular, right? But if that were not the case, then of course equilibrium statistical mechanics wouldn't make any sense, right? Then we would always have to say, well, if I prepare the system this and that way, and if I wait so and so long, then I could do this and that. But we are just saying I have something that controls the temperature, and once I know that, then I know what equilibrium is, no? And that's why Gibbs statistical mechanics is so powerful, that because you just know which state you're going to in the long time limit, right? And if you make a local measurement, you forget about your initial condition, because all the info is spread, and you see just this thing. It's really beautiful, I think, no, that this emerges. And MBL pokes a hole here and says, no, this is not happening always. Sometimes this is not happening. And that looks like now we have lost this beautiful, robust thing, but we gain also something. We gain that we can have some interesting structure, and that we can work with this structure. So it's always MBL is very difficult to describe. Eventually you have to describe the protocol, you have to describe the state and so on. But once you have that, you can do something useful with it. Here you can say, I have a simple recipe, but after all I have the state of least information of maximal chaos, and that's, it's a matter of taste what you want to achieve. Okay. But let me discuss this a bit to the end. Right. Let me make a side remark. If you have this was for Hamiltonian systems that are closed, but nowadays it's also very popular to look at time periodically driven systems, where you have, for example, a laser that periodically stirs the system, and these are called Floquet systems. And because you stir the system, so you have a periodic driving. That's especially interesting because you can do it experimentally in cold atoms. You can use lasers and so on, and shake your lattice in a periodic fashion, and then you can ask what happens there. Well, if you stir, then energy is not conserved. You can absorb energy, and if the system is thermalizing internally, it will always arrange itself to absorb energy from outside until it cannot anymore. And if you are at the temperature T roughly inside, you absorb, the absorption rate is always finite, and it goes down only as 1 over T as T goes to infinity. That's because when you are at infinite temperature, you are equally likely to be excited than not excited, so absorption and emission is balanced, but as long as you're not at infinite temperature, you still absorb. And so in a Floquet system that thermalizes, you absorb energy until you cannot do any more, and you go to infinite temperature. And that means the equilibrium state of a periodically driven system in a thermalizing system is just infinite temperature. And that means if you put here infinity, you get just 1, and that means every state is equally probable. And so why do I mention this? Because their energy is not conserved, so it doesn't make sense to say the outside of your system serves as an energy reservoir, or the say if you have no particle conservation, there would be energy conservation, and you could think the reservoir has the important role of giving you energy. That's sort of true, but what is most important, the role of the reservoir is not to provide energy, but to provide resonant processes. You want that the configurations inside A can really change forever because of processes that take place. It's not so important that you exchange energy, that comes along with the fact, but what is really important is that you have resonances here to have thermalization. So that's really the what drives thermalization. And if you kill the resonances, what happens in MBL, then you don't get thermalization, in a nutshell. Okay, now let me discuss this now eigenstate thermalization hypothesis. So, which is then broken by MBL. I'm sure many of you have heard this term, eigenstate thermalization hypothesis. So, which goes back to Deutsch and Srednitsky in 91, Srednitsky, both in Santa Barbara, I think. So if we say essentially any initial state of a given energy will eventually thermalize in this fashion, then this is certainly also true for an eigenstate. If I could prepare an eigenstate, but that's essentially impossible. Let me tell you that experimentally you can never prepare an eigenstate, so it's a theoretical construct, an eigenstate, but understanding eigenstates lets you understand dynamics, and that's why we care about eigenstates, even though in an experiment you never prepare an eigenstate unless maybe a ground state of a ferromagnet or something simple like that, but generic eigenstate is a completely theoretical idea that never is realized in a lab. Okay, but here we can say if this happens for any energy state with energy E, let's take an eigenstate. And what is the time evolution of a density matrix of an eigenstate? Alpha, so that starts, that's this thing here. What is the time evolution of this thing? It's constant, right? Because the density matrix evolves like this, right? And these are eigenstates, so you get e to the minus right, and so these phases go away, and so this is just constant, right? And so in particular, if nothing changes, then it doesn't change the infinite time limit either. And so this must, in the thermodynamic limit, apparently, is just if I take this and I trace out the rest of the system, then apparently I get the rho equilibrium A. Right? So if this hypothesis is correct, that typical energy states go to equilibrium, it must hold for eigenstates too, and that means that the reduced density matrix of an eigenstate is actually equilibrium. And so this is known as ETH. It's a hypothesis of eigenstates basically representing local equilibrium. And it's kind of funny if you think about this, no? You have so many eigenstates at a given energy density, and each of them is orthogonal to the other, but if you look locally, they all look the same. It's sort of interesting if you think how this comes about, no? But on the other hand, this is just the extreme limit of the microcanonical ensemble. So you remember how the microcanonical ensemble goes. You basically project onto an energy window that is very narrow around a given energy, and then you say I have equal likelihood of the eigenstates in there. In the limit where you take a window with just one state, you get this, and then this is the microcanonical version of Gibbs statistical physics, right? And the statement is then just the equivalence of microcanonical ensemble and canonical ensemble if you go to subsystems, and that you understand pretty well. But maybe formulated like this is still sort of speaking to you in different terms, even though you know that pretty well, that this should be holding, okay? Now, you can ask to what extent is that, you know, if I take a finite system, how well does that work? This works in the thermodynamic limit, right? The eigenstate thermalization hypothesis also goes a bit further and says if I take two eigenstates and a local operator between two eigenstates, how does that actually behave? So these are at basically the same energy but different eigenstates. Then you get the expectation value of this operator in the Gibbs ensemble when these states are the same. And then you have, and otherwise essentially zero, and then you have E2 minus S of E entropy at this energy that you're considering times a certain function, a smooth function of the average energy and the difference. Okay, and then some random factor. Okay. So if you have a finite system, there is a finite small, exponentially small fluctuation here. You can wonder why is it exactly like this. So the number of possible eigenstates that you can put here is basically e to the SE. So the number of eigenstates, relevant eigenstates is e to the SE, and so here you have basically 1 over square root of NES, and I let you figure out why it's exactly like this and not some other scaling as the thermodynamic limit is taken. This makes sure, this strong separation, this thermodynamic limit makes sure that essentially you have no fluctuations of operator expectation values. You know, eventually in the thermodynamic limit you have to make sure that everything looks the same, so you cannot afford big fluctuations when you take superposition of eigenstates, right? If I take A times alpha plus B times beta, then or a longer superposition of equal energy eigenstates, then I should still get that. And in order to get that, I have to make sure that these off diagonals are relatively small. But of course I can prepare an initial state that has a certain energy which has a very non-equilibrium texture, right? So an operator might have an expectation value in the initial state which is not at all thermal, not at all this value. And to achieve that, you have to make sure that these fluctuations are sufficiently big so that you can construct initial states that are non-thermal. And yes. Mm-hmm.
But there are different eigenstates with the same energy.
Mm-hmm.
Is all the local operator?
Yes.
Okay,
Mm-hmm.
then alpha and beta for the local system, they have to give the same. I mean, by hypothesis, so we're assuming hypothesis, right? Then they have to give the same reduced density matrix.
Mm-hmm.
And then effectively for a local operator, maybe those will be the same states. So why do we have? Why do we require those two states are identical, if they give the same state locally?
Why do we have to?
Why large system state alpha and large system state beta have to be identical?
Why this term?
Why delta alpha?
Be so if this is so what would you want to write? You want to drop this term or?
I would want to write delta E alpha E beta. But they have to be the same energy. I know.
Yeah. Okay. This is basically understood that E alpha is almost equal to E beta. Here, when I write that, so otherwise, or you can put that into this function. If E alpha and E beta are very different, then this argument becomes large, and then there's a suppression. And of course, this matrix element must be zero if alpha and beta are a totally different energy, right? And a local operation cannot change the energy by much. And so,
They have the same energy but different states.
yeah.
Will it have a matrix element?
A very small one, right? This is gone, and then you have this very small matrix element. There should be a matrix element, right? And it should be somehow small because it's like a random matrix problem here. This is essentially a random matrix. This so this factor is pretty random, and then right. Okay. Anyway, so if you like to think about this, maybe you want to figure out why exactly you have to put this and not something else. But that's a bit of a sidetrack. So now, what is happening in thermalization? If you prepare your system in an arbitrary initial state, which is a superposition of many eigenstates, right? Typically. So you have unitary evolution, so you just get here e to the minus e a t, and here e to the minus e a. So what happens is that in the initial state you may have pretty precise correlations between these coefficients, so that certain expectation values are of operators are actually non-thermal in this superposition. So, for example, if you prepare an antiferromagnet in a ferromagnetic state, or if you put your particles all on one side of the system, then you would have a totally non-thermal expectation value. But then, in the course of time, your eigenstates will dephase. That means they acquire all different phases, and then this subtle correlation of the coefficients is lost. And then after that has happened, you can still get back this result. So even initially, you're very far from that. So if you're at the time zero, you would not be at all in an equilibrium. But once you have dephased between all the eigenstates, then you get back your thermal density matrix. That's essentially what happens in thermalization, right? So this whole thermalization hypothesis, which is sort of an interesting way of talking about how you get the Gibbs ensemble, motivates to look at these eigenstate ensembles. So at this rho alpha, which are these psi alpha, and if you have a thermalizing system, it sort of doesn't give you more information than that. But what is now interesting, so this is basically the same as the equilibrium one for thermalizing systems. But when you have MBL, then it's not at all the same. So then rho alpha is not the equilibrium one, and it's one of many possible infinite time stationary states that your density matrix can have. So in MBL you have a much larger variety of what your long time density matrix will look like. It depends on the initial state, and it's actually pretty hard to determine what it will be. But in principle, you can figure it out. So for MBL, it's still actually expected. I think one can maybe even, I'm not sure one can prove it, but it's expected that your density matrix will tend to some infinite time object. But this object is not a single parameter thing, but there are many, many parameters that go in here. And depending on your initial state, you get something else. If you can figure out how to get from initial state to this and how to make this translation, that would be a great step forward. I think that is not achieved in the field, and I'm not sure it can be done without fully diagonalizing the system, but it is possible that there are ways that you would get that. And of course, that's of a great interest. You want to understand when you prepare your system in a clever way, what will you see at infinite times, and what information is still sitting in here, and how can you efficiently describe that? Yeah. Yeah. Right. Mm-hmm. Mm-hmm. Yeah. So maybe your question. So what can this be? This can in general be sum over all eigenstates, and then you have here weights, and then you have rho alpha here. So this is going to be the most general stationary state that you can expect, right? Which doesn't depend on time anymore. These are certainly time independent. Anything else would be time dependent. Now this is a not interesting thing to write down here, because every rho alpha locally looks like rho equilibrium, and so this just becomes rho equilibrium again, right? But in MBL, since all these, I will show you directly that this is so, in MBL all these are different, so you have a huge variety of what you can get in the long time limit. And as I say, this how to get from initial state to this and to determining the p alphas, or have a better representation of this thing, that's an unsolved problem. But that it exists is out of the question. So it certainly does, and you can already discuss phenomenology. But if you want to sort of really use the tool and then make predictions, if I use this and that protocol, I will see this and that at infinite times, then that's sort of a machinery that, you know, you can solve the whole system, you can solve the whole Schrödinger equation, diagonalize the system, then you get the answer. But is there any shortcut? We don't know at this point, I think. Yeah. Yeah, that's what you, that's the gut feeling that one has, and that would be so in the pure Anderson model without interactions. But then we'll discuss that with interactions you still have dephasing actually. So you have dephasing that is much slower than in the fully thermalizing system, but eventually it will take place, and that means that your local region A will still sense something of outside and get entangled a bit with outside. Not as much as if you're thermal, but still enough to completely kill phases. So I think this is generally true, that you get something that is time independent here. But maybe this becomes clear when we discuss in more detail dephasing. Okay. So now we have a quarter of an hour left, right? Then a bit less. Okay. So, but let me start giving you now the flavor of how one convinces oneself that MBL is a actual possibility. Okay. So now we think we know what thermalization means. Now we want to poke a hole in it, right? So we said we need no bath, not an external bath, and that means actually no continuum, right? And so there are many continua around. There are phonons, but there are also photons. So the electromagnetic continuum is bad. You have to throw that out, or you have to have some fancy stuff to localize phonons by superconductivity and so on. But that's extremely difficult. So no goldstones and no gauge bosons, basically. In particular, no photons. And then we don't want the continuum inside. And how do you do that? So you ask, is the Fermi golden rule working or not? And you want to actually argue it is not working. Try to show no, right? And that's always the same strategy in localization. You always try to show that that there is no continuum, that you are localized. If you try to show the opposite, that's extremely hard, and the mathematicians cannot show that even in the 3D Anderson model. When you go to weak disorder, if you're supposed to prove that there is diffusion, which no one of us doubts, but if you want to prove it, it's extremely hard, and I think it's not fully achieved, even in the non-interacting Anderson model. So what is much easier is to show that when the disorder is strong, then you're localized, right? So you want to show that you are not connecting to a bath, you're not establishing a bath, okay? Right, and now let's go once more to the golden rule. I think here we can write it once again in honor of Fermi. So we have this expression, sum over final states, MFI, matrix element squared, delta EF minus EI. Okay, and now you want usually to replace this by this. By a density of states here, of final states. But now if we talk about, for example, a spin system or just electrons that are localized and therefore have a discrete local space, then this sum here will always be finite if we only take matrix elements with the nearby spin. So if I have a spin here, and it interacts with this spin and this spin, and then maybe these interact with something else. If I take first order perturbation theory, then I can only connect to these spins, right? And then there are so and so many final states, and in principle this looks always like a discrete sum, and so it looks like, well, how could I ever get something finite here? Well, the clue is that you have to go to higher order perturbation theory, and then you get more and more states and less matrix elements, and then you have to see whether in the process of infinite order perturbation theory you get large enough matrix elements and small enough level spacings in your final states, or whether the matrix elements die off too quickly for the spacing of the final states. And when the matrix elements win, you get basically delocalization. Then you connect to infinity, because at infinity you have so fine level spacing that you are still resonant, or you don't when the matrix elements die off too quickly, and then you are basically only seeing a local environment, and then this sum is zero. So the strategy that already Anderson invented in his 58 paper, it's a beautiful paper actually to read, so much physical insight. I really recommend you to read it. He was exactly asking this question: what is the imaginary part of the self-energy, which is nothing else than the decay rate of a particle? And he realized that he has to calculate the self-energy, basically this decay rate, to infinite order, and he has to ask whether the perturbation series converges or not. If the perturbation series converges, it means that when you go to high orders of perturbation theory, this dies off, and then and essentially you never get the resonance, and then you get just a self-energy that is only real, so it only renormalizes a bit your local level, but it has no decay rate. But if it diverges, it means that you can go further and further out, and if out here you really couple a bath, say a phonon or so, a phonon bath, then and if your perturbation theory doesn't converge and grows and grows as you go on, then you reach this bath, and then you finally can decay. So that's really the idea of localization, trying to show that your perturbation theory converges and that you never have to worry about infinity, right? So you want to argue that perturbation theory remains essentially local, and everything else is just exponential decays that you don't have to worry about if your system is infinite. Well, you don't want photons in your system, or because photons also don't localize, they form a continuum. So if you have charged particles that can emit or absorb photons, then localization is in principle gone. Yeah, so I say you cannot afford a continuum, so you shouldn't put the continuum in the first place. If you couple your electrons or spins to phonons or to Goldstone modes or to photons, then you know that you will not be able to prove localization. There will be processes that are always resonant because the photons or the phonons have a continuum spectrum. So the Fermi golden rule will always work because this sum is always an infinite sum over finely spaced final states, and so there is always a decay rate. It may be very small, but it's always finite. So if you want to prove something to yourself, then you have to say, I neglect all those couplings, and it's like these degrees of freedom are not there. Then you get some answer, it works or not, and then you can worry in the end, well, what about if I think that there are still phonons and photons? And then you will get a statement like, on the time scale on which phonon coupling can be neglected, you see something like many-body localization. And on longer time scales, of course, the phonons will take over. But then you can say the transport will be limited by electron-phonon coupling, and that therefore it's very weak, and therefore blah, 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 right? So that's a bit the logics. Right. So now you say, okay, but this is daunting to do infinite order perturbation theory to establish whether I'm localized or not. And actually there's a shortcut. You can already basically tell at first order of perturbation theory whether things are working or not. And that's actually what Anderson and Fleischmann were doing, and they got most of things right. Actually, maybe even more than later on, until we understand that was 82. So they did essentially first order perturbation theory. And so what do you have to do? You have a certain excitation. For example, you have your spin that is up, and you want to ask, can it flip down? Then you have you have this process where the spin goes to down, and the neighbor spin, for example, flips as well. Okay. Now there is a certain energy cost to that, because say there is a local field H1 and H2 acting on these spins, say something like that, and let's take Ising spins. Okay, and so you pay something like H1 plus H2 when you flip the spins. But there is a certain amplitude to do that, because you have a term in the Hamiltonian, say, which is S1x, S2x times some j, right? So there is a 1 to up to down process with amplitude j, right? And now what you basically have to compare is this matrix element bigger or smaller than the energy gap. It all boils down always to the same question, whether you are resonant or off resonant. The only extra difficulty is that you have not only one partner to go to, but you have quite a lot of partners to go to. You have a lot of things that you can do. You can flip this spin and that one, or maybe if this is not spin 1/2, you can only turn it a little bit, or you have other neighbors, or maybe you have 2 spins that you want to flip, and so on and so forth. And you have to make sure that none of these processes is resonant. But once it is resonant, so if J for one of these processes is bigger than delta E, then this means that you hybridize between the two configurations, hybridization. So that means if you try to construct an excited eigenstate and you say, I believe my eigenstate looks more or less like this, but then you see that you have a resonant matrix element that connects to this configuration, then you know that your eigenstate will be a good mixture of these two at least. And then you go on and you ask, well, now can this spin maybe flip back and flip the other spin that was here and make this up? So then here you have another delta E and another J, right? And so you have to go and see whether you can percolate through many body configurations in a resonant fashion and get out to infinity or not, right? And the idea of many body localization is just to argue that under certain conditions you have too few such resonances, such that maybe locally you have once in a while a resonance, but then you're stuck there. Then you cannot use any of the connected spins that you touched and have another resonance and move further and further. And if you cannot do that, then you would pretty likely conclude that things are localized. So you try to argue that resonances do not percolate. Okay, and what is important in this, you see now you're not working with a single particle. A single particle, it's always that particle that you have to argue about. So you say first it is here, and then you say maybe it's resonant with this side, and then maybe it's not resonant with that side, but maybe it can tunnel over here, and so on. Then you try to construct a resonant network that goes to infinity. Here you have a lot of degrees of freedom, and you don't always have to touch the same degree of freedom. You don't always flip the same spin. First you flip these spins, and then maybe these spins, and then maybe again that, and then this one. And the question is, does this avalanche of hybridization processes, does this form a network that goes out to infinity, or is it sort of only local? And well, the state of the art is a bit that you are trying to to show that this doesn't percolate, and then you get localization. But maybe, well, you feel again from my way of how I formulated, I know that this is not quite working, but it gives you a very good feel of the qualitative physics. So when you find that it doesn't percolate, then it's for sure that then the dynamics in the system, even if it should turn out not to be fully localized, it will be very slow, right? So if you find that as you tune parameters, as you tune your disorder, which is these fields here, versus exchange terms, if you find that as you make the disorder bigger and bigger, you get less and less resonances, and then you don't percolate anymore, then you know that transport will have a very strong crossover there. Maybe before you have good spin transport, and then you have extremely bad transport. Of course, MBL would say the transport is exactly 0, and so now you have to work harder to really show that transport is exactly 0. But this type of qualitative consideration will tell you that at least there is a strong crossover. And so in the next lecture, I will quickly show you what is the argument of Pasquale and Altschuler for disordered electrons to identify this crossover and to come to the interesting idea that there could be a temperature-driven crossover. Or not only could, that there is a temperature-driven crossover, and then we will ask what about worries beyond this simple picture. And I'll also present you some ideas of the rigorous proof by John Imbrie, where he showed that much beyond this kind of consideration, you can actually prove that in one-dimensional spin chains there is MBL. So it's not just sort of perturbative on this level of percolation, but really you can make sure that things do not spread to infinity, and then you can prove that this happens. So that's for next time. Are there questions now at this level? Yeah. Yeah, sorry, maybe I didn't make the point clearly enough here. So you can ask yourself when does it work, and then I sort of said, well, it can only work if you go to infinite order and so on. But actually, it works self-consistently once you check that your matrix element is bigger than the final state level spacing. You see, you can say, well, the density of states here, this will roughly be 1 delta E, the minimal delta E that you get, right? That tells you how is the spacing of possible final states. If this, and this is J basically, and so now you get the decay rate, which is roughly J squared over delta E. And now you see when J is bigger than delta E, then this decay rate will be bigger than J and also bigger than delta E. And that means that you have an energy uncertainty of your degree of freedom, which is bigger than the spacing in your final states. And that is the condition for the golden rule to be self-consistent. Because if this spin has an energy uncertainty like this, right? That's the decay rate. So it doesn't make sense to speak of a local spectrum that is sharper defined than this scale. Then it also will hold for the next spin. So if the next spin has this energy uncertainty, then I shouldn't define these delta E's on a finer scale than this, right? And then the discreteness is gone, you see. So if you can argue that all the degrees of freedom have energy uncertainties that are bigger than the delta E, then you're self-consistently sure that your environment is actually a continuum and doesn't look like delta peaks. And so at the hand waving level, what you have to do is you do first order perturbation theory and you check whether your matrix elements are bigger than final state spacing. If yes, then you know that the self-consistently the environment will become a continuum because the lifetime of your neighbor is shorter than the inverse of the level spacing of the next neighbor, right? And so even though it looks like you have only one neighbor on the discrete spectrum, but this has a finite lifetime self-consistently, and that smears out the local spectrum, and then this becomes a bath. And then it's self-consistent to say, okay, Fermi golden rule is fine, and the system will equilibrate. But if you don't have that, then your neighbor will have a discrete spectrum, and then it all doesn't work. Then it breaks down. That's basically the philosophy. But we should now really make a break. Sorry.